Welcome to the course. Today we're going to talk about lazy evaluation. I'm going to show you how to run your programs in a lazy way. Lazy, it means that the program does the minimum amount of work. Okay. First, before we start, a few seconds of respect for the Ukrainians who are fighting for our freedom and for theirs. Okay. Today we're going to talk about lazy evaluation. I'm also going to show you some running code. But first, I have an announcement. The lab sessions. There are 3 lab sessions. They start next week, Monday and Tuesday. You only have to go to 1 lab session per week. Okay, the Monday lab session is 8:30, 10:30 in auditorium Mercator 14. The Tuesday one is from 14 to 16 in Mercator 12. And the second Tuesday one is from 4:15 to 6:15 in Pierre Curie 04. Okay. I announced that there will be a bonus point. We will take the presents. So if you attend 1 lab session per week for the whole semester, you will get 1 extra point on the exam. And if you miss a few, it's not a problem. It will be pro rata. So if you attend 80%, you will get 0.8. Okay? This is to encourage you to attend the lab sessions. That means it is technically possible to get 21 points on this course. Okay? Because that bonus point is an extra point. And there have been people who got more than 20 before, previously, so it is possible. You only have to attend 1 out of every 3 per week, because we'll be doing the same exercises in each lab session. So Damianas Koke is the teaching assistant. He will also send mails explaining this. So the presents will be taken at the lab sessions for the bonus point. And we expect you to try to do exercises. If you just go there to look at videos, we will ask you to leave. Okay. So you have to do exercises. Okay, so today we're going to talk about a whole new paradigm of functional programming called lazy evaluation, and I'll show you lots of programs. And it's really a weird and different way of thinking, but it's very powerful. And there are languages that are based on this. The most famous language based on lazy evaluation is called Haskell. And this language has a large community of people programming it. There are even cryptocurrencies built in Haskell that make a lot of money for now. So this is actually a very big thing. And if you learn lazy evaluation, it will help you a lot for Haskell, but also for many kinds of programming. The lazy evaluation is very powerful. Okay. Let me first give you introduction. Then I'll give you the semantics. The lazy evaluation is a very natural extension to the deterministic data flow. It's actually very simple extension. One new operation we add, and it's very powerful. Okay, let me first give a simple introduction. So a lazy program looks just like a functional program, functions, okay, but it executes in a different way. When you call a function, it is not evaluated, not right away. For example, if I define the function lazy add, and the way to do it in Oz is to annotate fun by typing lazy after that. if I do lazy add of x, y, and all it does is x plus y, it's just an addition. If I then do lazy add 1020, s equal lazy add 1020, you expect the result to be 10 plus 20, right? And it is 10 plus 20, but not right away. When I call this function, nothing is done. Well, actually, something is done. Internal to the system, it sets up something called a lazy suspension, but the computation is not done. Okay? And I have to show you how this works. Where is the system? There should be a system. Just a second. Okay, I'm running Mozart 1.4.0. Let me start it again. Where is it out here? Okay, so here it is. This is Mozart 140. Which works very well here. I have to explain that there are two versions of Mozart. There's Mozart 2, which is the one that I expect you to run, which is available on mozart2.org. But there's also a Mozart 140. But I'm running it inside Docker. And the reason is that Mozart 2 is 64-bit system, and Mozart 140 is an older system, it's 32-bit. So it will not run on the 64-bit, so I'll run it inside a virtual image here. But Mozart 2, this is an old Mac OS, Big Sur, and it has a bug, and Mozart 2 does not run very well on Big Sur. So that's why I'm running Mozart 140, just to explain. But here now, I will show you the example. I define a lazy function. 10, 20, sorry, on x, y, x plus y, okay, file this, and now I will call this okay. Run this. Look what it displays. It displays S. Let me make this bigger. It displays, it doesn't do the addition. So what's going on? Well, it actually will do the addition, but only if we need it for a computation. The browse is a special operation. Browse does not need its value to display it, okay? But I can do something else. If I do browse s plus 100, now I'm doing an addition, plus. And the plus needs its two arguments to do the addition and to browse. So the plus needs S, and this is what will trigger the computation. This is lazy evaluation. So if I execute this browse s plus 100, then the lazy add will run. Okay? So let me run this. You can see now it displays 130. But the first s also, of course, is updated. That's 30. And it's because of the addition needing the result. So this is the idea of lazy computation. You only do the computation if somebody else needs it. So when I call a function, it's not executed until somebody else needs it. Okay, so that's the intuition. I have to explain exactly what it means. What does it mean, needing the result? And how do we use this for programming? Okay, so that's what I'm going to explain to you today. And to do that, I will explain first the semantics, so you understand exactly what's going on. This is actually very simple. Okay, so here's the lazy add. How does the lazy add work? The way always we do this is we have to look at the basic underlying simple language inside. Okay? This is the kernel language for Oz. Of course, all languages have this, even if you don't see it. Okay? But in Oz we see this. The lazy add function turns into a procedure. Remember that? With one extra argument, which is the output. Lazy add x, y, r. And it creates a thread, and in that thread it does wait needed on r, on the result. And then it does the computation, r equals x plus y. You see that? It creates a thread, and inside that thread it does a new operation called wait needed. So what is this wait needed operation? This is one new operation we add now, okay? Remember how we defined programming paradigms? We start with a simple language and we add concepts, okay? This is what we did in the course before. And we're going to do that here too. Wait needed is just one simple operation that's added to deterministic data flow. So what does the wait needed do? Wait needed is a very interesting operation. Wait needed R will suspend, that means it will wait, it will block the current thread until another thread needs R. Okay? Until another thread, for example, has to do R plus 100. And the plus needs its two arguments, and that will cause the wait needed to continue. So the wait needed waits until somebody else needs the result. So that's a very interesting kind of operation. And if you've never seen this kind of operation, you have to think a little to understand really what's going on. Okay? To be more precise, what does need mean? I say it waits until somebody needs. What does need mean? We make a very precise definition of need. A thread needs R if it waits, if R has to have a value. If R has to be bound to a value, and this is an operation called wait. Wait will wait until R has a value. Okay? This is a data flow operation. So if the thread does wait R, that means it needs R. Okay? And that means the wait needed will continue. So wait needed waits until some other thread does wait. See how the interesting kind of connection between those two operations. Okay? Let me now try to make it more complete. To really explain how this works, let's now go back and look at how the data flow works, how the deterministic data flow works. So let's say I do S equal S plus 100 here. Okay, X plus Y, so X plus Y. So that's a data flow. It waits until X and Y are values and it does an addition. How does it work? Well, actually, it's in the low-level system, it's translated like this. So S equals x plus y. It waits on x, it waits on y, and then it does a primitive add. This is the add of the machine, the add instruction. And this gives x plus y into v. And then it binds v s to v. Okay? So there's the wait and the bind. So this is the regular data flow. And if somebody else does a wait, then it will wait until there's a bind. Okay? So wait and bind are connected. So if I do s equal x plus y, and then I do t equal s plus u, where this one needs the s, this one will do a bind of s, but this one will do a wait. It will wait for s. So wait s will wait until somebody else, another thread, does bind. This is the regular deterministic data flow. So this is how it really works. Okay? Underneath, you have these two operations, wait and bind. Okay? And wait, and the operation wait will wait until s is bound to some kind of value. And many operations have to wait. Arithmetic, of course, has to wait. Case statements have to wait. If I do case L of h bar t, it waits until L is bound to a list. So the case also has to do a wait, because it needs L. Okay? And other operations too. If I do a function call, f of x, remember functions are values. It has to wait until f is bound. Because if f is unbound variable, this you cannot call. So it waits until f is bound. Or the dot operation, if r is a record, r dot name, it has to wait for r. Okay? So you see, any operation that needs, it has an input, will need that input. Okay? So the wait needed operation is added to that. It's a third operation. You have wait, bind, that's the regular data flow. And to make it lazy, we add a third one called wait needed. And wait needed will suspend the current thread until another thread does wait x. Okay? See how wait needed works? So semantically, all the examples we will see today will be explained like this. I will show you some really neat code today, doing really neat stuff, and it looks like magic, but all the magic is here. There's no other magic. Okay? The new spell I'm teaching you is just wait needed. That's the only new thing we need to do everything I show you today. Okay? Okay, here's a simple example. You can actually use wait needed directly. If I do wait needed x, x equals 100, sure, I can do that as code. That will, if I do browse x, it displays an unbound variable. But if I want the x to be bound to 100, I have to need x. So I do x plus 0. Okay, that will need x. See how interesting it is, huh? Okay, I'm not sure how this, how do I get the, I have not ever used this in a, so the mean fact of leaving, it's back. Okay, good. Okay, so Docker and X11 is a very strange system. Okay, so let me do something here. Declare X in wait needed X equal 100. Okay. So this will bind x to 100, but not right away. Okay. If I do browse x, it displays x. Okay. Because the weight needed, nobody needs x. So the weight needed will suspend. If I want to force the x to be bound, I have to need x. So I can do x plus 0. Magically, it works. See how that works? So that's the basic idea of weight needed. Okay? So in general, when you do fun, lazy, so in Oz you define functions using fun. If you do fun, lazy, it will create a lazy function. So it does a different translation. So don't worry, I will put these slides on the Moodle today. So these slides are very new. I made them yesterday, okay? So, because last year there were no slides. This is a new course. So there is a video on YouTube of last year's course where I explained this, but with no slides, okay? I just write things on the board. So now I have slides. Notice that the function fx1 to xn is defined as a procedure with r added, extra argument. It creates a thread. It does weight needed r, and it does r equal the expression. So every lazy function is defined like that. Okay? That is the general translation scheme for any lazy function, just to show you. So when I define lazy functions, I'm just doing this, okay, actually. The system is doing this. Okay. Okay, so that's all very good. Now I want to show you some programs. I want to show you some programs to show you what you can do with lazy evaluation. Because I just showed you the principle, but what can you do with this? Let me show you now, really, to the different kinds of things. A simple producer-consumer. Okay? Producer, it produces a stream, and the consumer will read the stream. Remember, this is what we saw already, yeah? There's nothing new here. Here's a producer, L to H. So it creates a list from L to H. But I add delay 1000, so it's creating it slowly. So it creates a stream. If you run it in a thread, it will be like incrementally growing, okay? And the consumer will read that, and it accumulates, it will add all the results, and it will create an output stream where it has added all the results that it sees, okay? And I will show you 3 ways to run this code, this producer-consumer. We run it sequentially, we'll run it as data flow, as what we did before, and we'll run it lazily. And you'll see how the same program will run in 3 different ways. All 3 ways are correct, okay? All are declarative, so they all are functional programs. They all are technically doing lambda calculus underneath, okay? They all obey the Church-Rosser theorem. What this means is that a functional program, a lambda expression, will always give the same result, no matter in which order the reductions are done. Okay? All reduction orders give the same result. This property is sometimes called confluence. This is the main, very strong property of functional programming, why it's not non-deterministic. It's because of this very powerful theorem. All 3 ways that I'm going to show you now, they all will give the same result. And in fact, we are just taking advantage of Church-Rosser. The 3 ways are just executing the reductions in different orders, in fact. They are doing the same work, but they're doing in different orders, but they will give the same result. Okay? So let me give you first the three ways, but then I will actually execute them to show you how it works. Okay. So the first way, so first let's look here. Huh? We have a producer which creates a list from L to H, 1, 2, 3 up to 10, for example, and the consumer which reads it, and if there's a nil, it stops. Okay? And gives you the cumulative sums. Okay. Let's now do sequential execution. Prod 110 and consumer starting with S1, okay, and we browse both of them. Okay? Okay, let me run this, and you see how it runs. It's important really to understand the difference between the three ways of running this. Okay? So I have here some code. Just a little bit faster. I don't want to spend all my time. So like this. It's not HD. I went to the title anyway. Okay, so I'm good. Here we have the producer and the consumer. Okay. Now let me run them. Browse S1. Browse S2. S1 equal to prod 110. S2 equal the consumer of S1 starting with 0. Okay, I will run this. Notice the producer has a delay of 1,000 milliseconds. That means when I run this, I will have to wait. Okay, so we should run this. S1 is 2. Okay, S2 is still nothing. Okay, ping. You see the result, S2 only appears at the end. Boom, the whole thing. So it's actually a sequential execution. Okay. So the result, this is, you can also call it batch. So we only see S2 when this whole thing is finished. And the reason is because it's sequential, executing sequentially. Okay. So that's the sequential. The second one, let's now, we execute them in their own threads. This turns them into concurrent agents, functional agents. Now we're running deterministic data flow. And it's not exactly the same as the sequential one. There's a difference. Okay? There's a difference. So what is the difference? Okay, somehow the Docker has disappeared. I know it's here. I'm good. Okay. No, it's this. So let me put this now in its own thread. And okay, let me go to browse. Notice that both of them now are growing at the same time. The output S2 is appearing incrementally. See that? And we only have to wait 1 second to see the first result. Okay, so that's a deterministic data flow. It becomes incremental. So what is the difference with sequential version? The deterministic data flow version is incremental, because these two are agents that are running concurrently. Whereas in the previous case, they're running sequentially. Okay? These two are running concurrently. Now let's run it lazily. And it's even different. Another different. But we'll have to slightly redefine the code. We turned them into fun lazy. But the functions stay exactly the same. It's only that they're annotated lazy. Okay? So what happens now? But nobody needs. So what happens is, the way it works is like this. Nobody needs S2 because the browse does not need. That means the cons, the consumer, is not run. So it has a case. That means nobody needs S1 either. That means both the producer and the consumer are not run. You see, the control goes back from the output to the input. Since nobody needs S2, consumer is not run, so nobody needs S1 either. So the producer is not run. So nothing is run, okay? Okay, I have to show you that. This time I have to annotate them lazy. I will have to recompile them as lazy. Okay. They don't have to run in their own threads. Because you could use lazy without concurrency. Yeah? So let me go over the house. And this. Nothing. Nothing. It just sits there. S1, S2. I remember in the two previous examples, the result was done. It was working. The first example, it was batch. So we saw nothing until 10 seconds because it's sequential. The second cons will only complete when the first one finishes, okay? Whereas the data flow one, the middle example, both of the producer-consumer are agents running in their own thread. So as the producer is creating the stream, the consumer will be consuming it incrementally. They're both running concurrently. But the lazy one is even different. I run this, and nothing is done because nobody needs anything. So how do I get this thing to compute? Well, I have to need the result. The only way to force a lazy program is somebody has to need the result. Okay? So how do I need the result here? Well, for example, I can do browse s2.1. The dot operation needs its result. Okay? It needs to know what is the list S2, or at least the first element. This will display the first element. So if I do this, a piece of computation will be done. See what happens? Now I did a little bit of computation. Just a little bit. But still, it stops after that, because these are recursive functions. When I do recursive call here, prod and const are lazy. So the recursive call will again wait until somebody needs. Okay? So the laziness is for all the elements of the list. So if I want to see the second element, 2.1, that's the second element. Then it will be computed. 1, 2, 1, 3. Now we do a little bit more computation. You see, the program is very lazy, okay? It will only do what really has to be done, no more. Now let me try to go a little bit farther. Here, I will ask for some more elements. Remember, there's still a delay of 1,000, huh? So this will cause some more elements to be computed up to number 36, which is the 8th element. So there's 7 2s here, and then a dot 1. That gives me the 8th element, huh? Which is 36. But the rest is not done yet. So you see how the lazy one works. It's, we go from batch to incremental to lazy. 3 different ways of running the same program. You see it, huh? Okay. Let me now, so that's one thing. I show you now the producer consumers. Question?
En fait, je pense que c'est déjà très bizarre, mais si on avait aussi besoin que la valeur dans la liste soit lazy, il faudrait faire une fonction à part qui est lazy, qui donne les valeurs dans la liste.
C'est ça. Si ici j'ai accumulateur plus H, si je remplace ça par lazy add, je peux. Hein? So the question is, the elements in the list can also be lazy. Yes. So this addition here is not lazy. But I can also make it lazy. I can replace the plus by lazy add. And then I will create the list. But until I really need the element, there will be unbound variables for the elements. Okay.
Et est-ce qu'il y a une fonction lazy pour chaque opération, donc lazy multi?
Non.
Non.
If you want to make all the, il n'y a pas de fonction lazy. De base, les fonctions ne sont pas lazy. La seule façon de créer des fonctions lazy, c'est avec fun lazy. Okay? Et donc, on peut faire, mais on peut donc faire. You can make any operation lazy by putting it in a fun lazy, of course. Huh? Even addition, it's even very simple operation, you can make them lazy. Okay? On peut faire tout lazy en le mettant dans fun lazy. Question? Oui, il suffit de mettre le mot-clé lazy, exact. C'est exactement la programmation fonctionnelle. So the question is, to make a lazy function, all you have to do is put the lazy annotation. Yes. So lazy is exactly the same as regular functions, program. Regular functions. So everything you know, still true. It's just that if you add lazy, it will delay the execution until the result is needed. So all the techniques of functional programming are still true, still valid. So it's just a new thing on top. Vous voyez, tout ce que vous avez appris sur le fonctionnel et sur le dataflow continue à être valable. Rien ne change. C'est juste que la fonction ne sera pas exécutée tout de suite. The function will not be executed right away, but only when it's needed. That's the difference. When it's executed. Le moment où il est exécuté, c'est la seule chose qui change. Okay? And the result is the same. Because of Church-Rosser, le résultat sera le même, il ne va pas changer. Tu vois comme c'est puissant, hein? Rien ne est falsifié. Tout ce que vous connaissez reste valable. Ok? Ça va? C'est pas mal, hein? Mais on n'a pas encore. So I still have not really shown you very powerful things. This is already simple things. But I will show you more powerful techniques. So lazy is interesting. It's like higher order. It's a simple idea, but it has very powerful techniques. Okay? So you can have eager and lazy streams. Okay? So I showed it to you. The first example was an eager stream, deterministic data flow. So the producer is creating elements. But in the lazy stream, it's not like that. It's the consumer that asks for elements. So sometimes people call it push and pull. So this is also a programming technique you can use. You can do push where you give values. That's regular deterministic data flow, which is eager. So all what we saw before, I will call it eager. En français, on peut dire tout ce qu'on a vu avant, ce sont des calculs ardents ou actifs. When you run the producer, it runs. Okay. But lazy is not like that. When you run the producer, it does nothing. It's the consumer who is the boss. Okay. So one way to see this, so here's a simple, I can make a simple diagram. If I have a producer-consumer, okay, or maybe I do it white, it's more readable. Producer-consumer, and there's a stream here. In the eager computation, the producer is the boss. The producer decides how many elements. But in the lazy computation, the consumer is the boss. The consumer decides how many elements. If the consumer wants an element, he asks for it. If he wants nothing, nothing is done. And if you want to terminate the computation, this guy decides when to stop. But in the eager, it's the producer who decides. You see, it's very symmetric. Okay? Everything you saw before, it's the producer deciding. Seems very normal, right? Producer deciding. All the programs you write before, in Java, everything, it's all like this. Question?
Oui, donc du coup, si je comprends bien, si on avait fait S1.2 par exemple, un browse S1.2, il se serait bien passé.
Si tu fais browse S1.2, tu vas forcer le calcul du premier élément de S1.
Et il se serait quand même...
Attention, tu parles de S1 ou S2 là?
S1.
Ah oui, si tu calcules S1, tu ne vas pas calculer S2.
Ouais, donc du coup, il va rien afficher.
En effet, il va juste afficher S1. So if you do browse of S1.1, that will force the computation of the first element of S1, but not S2. Nothing will be done for S2, because nobody needs S2. Personne n'a besoin de S2, donc on n'en calcule pas. Okay? So you should try it. So I recommend you try, experiment with this. If you don't understand, try it out. It's very easy. I will put all the code also on the Moodle. It's not there yet. So you can copy paste. But you can write, try this. So if you force the computation of S1, it will not force S2. Because nobody needs S2. But if you do S1.1, you need the first element of S1. But only the first element. Si tu fais S1.1, tu n'as que le premier élément de S1, pas le deuxième élément. Si tu veux le deuxième élément, il faut faire S1.2.1. Si tu ne fais pas ça, tu n'auras pas. So if you want something, you have to really say, I want this. Otherwise, it will not compute it. It's interesting, huh? The lazy. It's really different way of computing. And this is something you have not seen before normally, unless you write in Haskell or something. All regular programming language that you use normally will be doing this way, eager. If you call a function in Java, it will run that function. Seems very normal. But lazy is just the opposite. Okay? And it's just as interesting and it's just as important as eager. It's just that you don't have it in Java. Why not? Because the Java designers are lazy. I don't know. Because this is a very powerful technique. So lazy is just as interesting as eager. It's like a symmetric version of eager. Okay? Okay, let me show you more examples now. Let me show you how to compute with infinite lists. No termination. So laziness, because you only compute what you need, it means I can compute a list with no termination, an infinite loop. In lazy programs, you can use infinite loops. No problem. You can compute with infinite loops. You can build infinite lists. This works fine. There is no infinite loop in the execution because you only generate what you need, okay? So here's a simple function. Fun lazy ints n bar ints n plus 1. So this generates an infinite list of integers starting with n. So ints 1 will cause it to generate 1, 2, 3 forever. But that's not a problem in a lazy program. It's not an error. It's a perfectly good way of programming. Okay? Calling ints1 will just display an unbound variable. Okay, we can do it. I have to show you that. The nice thing about so where is the do I have to start the Docker again? So I guess Docker is not as great as people say it is. Okay, I'll have to start again the here it is again. Okay, so I will do so I'm lazy ints n followed by ints n plus 1. So this, you don't want to write this normally, huh? If you write a program like this without lazy, it's going to blow up the system, okay? The process will just blow up and eventually crash. But in lazy, it's perfectly normal to do this. Okay? L is equal to ints 1. How's L? Okay, so here it is. No problem. L. So nothing happens. If I want to see elements, I have to need them. So let's say I want to see the third element. That's L.2.2.1. The third element is 3. And now it computes 1, 2, 3. Okay, and then it stops again. It only computes exactly what you need and nothing more. Okay. Okay, I have to explain to you exactly how it works. So normally you already understand this because it's just using weight needed. But let me explain explicitly how this works to help you understand. Let's translate ints into kernel language. So ints n becomes ints n r, thread end, weight needed r equals n bar ints n plus 1. Okay, that's how it's translated. That's it. But it's a recursive call here. Right? Notice this is recursive. That means this recursive ints is also lazy. Huh? So if you do browse of r.1, the dot operation needs r. The weight needed will terminate, will continue, and r will be bound to n or 1 bar ints of 2. Okay? And what happens is, one element is computed, but there's a recursive call here. But this recursive call is also lazy. So it will immediately suspend again on another weight needed. So you see, when you have a recursive function, you actually have a whole series of lazy function calls. Huh? So if you do browse of r.1, you will only get one element, and the recursive call will suspend again. Okay? So recursive functions, it works very well with laziness. Okay? Okay, let me show you one other thing before the break. Okay. Okay, let's say I want n elements. I want 10 elements. We can define a function that will force you to get n elements. This function, in eager, this function is meaningless, okay? It doesn't have any use. But in a lazy program, this is a function that will force the evaluation of n elements of a list. And how does it work? It's very easy. So this is a function touch. Touch. So the idea is that you're touching the elements, okay? Tac, tac, tac. On touche les éléments. Encore un. You touch them. If n equals 0, then skip. You don't want anything. Otherwise, you do touch of L dot 2. So you do recursive call, but because you do L dot 2, you need L. L dot 2 needs at least one cons. It needs one vertical bar. So you will force the creation of one element. And then you do recursive call with n minus 1. Okay? To do n minus 1 more elements. So all it does is traverse the list. It doesn't do anything. It just goes down the list. But this forces the evaluation. See how lazy is funny, huh? It's a funny way. So if I want 10 elements, I have to do touch L 10 if I need 10 elements. Okay? Or touch L 20. Okay? Okay? Still here, very good. So here now I still have this ints. Let me define touch. Okay? Touch Ln. If n is equal to 0, then skip. Else, touch L dot 2 n minus 1. It's a very simple thing, huh? But it forces evaluation of n elements. Okay, good. Let's see how it works. Okay, let's do touch L 10. So L is what I displayed here. Huh? I want 10 elements. Okay. There you go. I have 10 elements. Okay? And they're there. They appear. Or maybe I want more elements. Touch 20. Now I get 20 elements. Okay? So with touch, you can, if I need a piece of the result, I can always use touch to get what I want. Otherwise, I get nothing, huh? So touch tells me I need something. Okay? So that's a useful function, a useful procedure when you are working with lazy lists. Okay. Okay, let me make a break now, but after the break, I will show you more powerful, I will show you some really interesting lazy programs. The first one we'll be having, but let me first do a break. On va faire une petite pause maintenant. Now, after the break, I want to show you some interesting lazy programs to show you the power of lazy evaluation and really why it's a real interesting way of doing things. And the first example I want to show you is something called the Hamming problem. So this is a famous little problem in programming incremental things. But first let me talk to you about the guy who gave his name to it, Richard Hamming. So this guy was an engineer who worked and a mathematician who worked at Bell Labs. So this was a famous place where they invented many things. I think they even invented the transistor there. And Hamming invented many things. And if you take courses, engineering courses, you will probably see his name appear. He invented something called Hamming codes for coding. He invented something called the Hamming window for signal processing, also the Hamming distance, and many other interesting things. Those are just a few of them. He wrote a really interesting book, which is called The Art of Doing Science and Engineering, Learning to Learn. And in that book, he kind of puts all his ideas from his own life, and it's really, really interesting. So if you really want to understand how somebody like Hamming, how he thinks, and really how you can be creative and do neat things and learn many things, this is a really good book. So I recommend this book, actually. But all that is just introduction. Today I'm going to talk about something called the Hamming problem. It's called the Hamming problem because Hamming presented it and he presented solution. And this was a long time ago. This was like in the 1950s. And in the 50s, this was considered a very hard problem, okay? It's in number sequences. It's a dynamic problem. And the thing is, you don't know in advance how much you need. So you're computing something, and it's incremental, and you keep going, but you don't know how much you need in advance. You have to keep going until somewhere, okay? But you don't know how much. So you cannot allocate a static array, for example, for this, because maybe you overflow the array and it's wasted, okay? So this kind of problem where it's incremental and you do not know in advance how much you need to do, it's a typical lazy problem where you can use lazy evaluation. This is really a perfect problem for lazy evaluation. I will show you a really simple solution for this problem, which is very efficient and uses lazy evaluation. Okay, so let's explain the problem. So you have numbers of the form 2 to the A times 3 to the B times 5 to the C. So A, B, and C are integers that are at least 0, okay? And actually, the general problem is where you have any number of primes, okay? But we'll do with 3 of them. You can generalize it if you want, because I want to show you the full code, huh? The problem is, I want to compute the sequence of these numbers in increasing order, without missing any. So it starts 1, 2, 3, and then 4, and then 5, and then 6. 7 is not in there. No 7. 8, 9. 10 is in there. 2 times 5. 11, no 11. 12 is in there. 13 is not. You see, so you have to keep generating the numbers, all of the numbers like that. But the problem is, when you know A, B, and C, you don't really know how big the numbers are. So you have this bunch of numbers, but you want to present them in increasing order up to a certain point. But you do not know in advance how many numbers must be computed. You have to keep going for a while. You don't know how far. So your program has to work for any number of sequence. And you just have to keep going, and then you stop somewhere. The program should let us compute those numbers incrementally until we're happy, until we're satisfied, until we're done. And it should be efficient. So, for example, allocating an array of fixed size is not going to work, okay? Because if you need less, it's waste. And if you need more, then the array is not big enough. So that's a very bad way of doing it. It's completely dynamic, okay? This is a typical problem where lazy evaluation is the perfect way of writing this kind of program. Okay, so here's the idea. First we need to make kind of an idea. How do you generate the numbers in increasing sequence? So here's an idea. So let's say I have my sequence, which is H, which is like a stream. 1, 2, 3, and then X is the next element, but I don't know it. So how do we figure out the next element? Well, it must be either 2 times a previous element, or 3 times a previous element, or 5 times some previous element. Because we're incrementing the A, B, and C here. If you remove 1, if you do a minus 1 or b minus 1 or c minus 1, you have a previous number, which is smaller. So the next number x it has to be either twice the element of times the previous number, or 3 times the previous number, or 5 times the previous number. So it's one of those 3 cases. So in order to determine x, we can look at those 3 cases. And so what do? We derive 3 sequences, 2h, 3h, and 5h. 2h is twice the elements, 2, 4, 6. 3 is where we multiply them by 3, and 5 by 5. So we have these 3 sequences. And we look at them. Notice 2 and 3 are already taken. So the first numbers that are not used are the ones in red. 4 is not used, 6 is not used, and 5 is not used. That means x, it has to be either 4, 6, or 5. See that? It's the first one that would be a multiple of 2, 3, or 5 of a previous element. So, because it's the first one, it has to be the minimum, right? So x is the minimum, of 4, 6, 5, so it's 4. And then after that you keep going. So the 4 is used up, then you have 6, 6, and 5, so the next number is 5, okay? Then you have 6, 6, and 10, so the next number is 6, and so on. And then you keep, and each time you use a number, you go one farther in the sequences. And so you can keep going with the x's. So once you determine x, you can determine the one just after x, huh? Or maybe I can show it here to show you more precisely how it works. Okay. So h is 1. We know it has to start with 1. Okay. So we have 2h, 3h, and 5h. So 2h is 2, 3h is 3, and 5h is 5. The smallest of these is 2, so the next one has to be 2. Now we have removed the 2, but now we have 1, 2. So this one turns into 2, 4, this is 3, 6, and this is 5, 10. Now we have 4, 3, 5 are the smallest, so the next one has to be 3. So we remove the 3 here, and now we have 2, 4, 6, 3, 6, 9, and 5, 10, 15. Okay? So the next one after that is the smallest 4, 6, 5. So it has to be 4. Okay? And then, so we get rid of the 4. So let me continue a little bit. So this will become 8, 12, and 20. So the next one after this will be the smallest of 5, 6, 6, so it has to be 5. Then we have 6, 6, 10, so it has to be 6. And the 2 6s go away. Then we have 8, 9, 10, so it has to be 8, and so on. Now you see how it works, huh? So the 3, you're going farther down, and each time you take the smallest one. So this is nice, huh? Now we can program this with lazy lists. It's very easy to program this with lazy lists. Okay, so let me show you how it's done. We need 2 operations. We need to multiply the list by some integer. H goes to 2h. We also need to merge ordered lists. So in merging 2 ordered lists is you take the smallest element, and that's the new one, and you keep going. Okay? So the result is also an ordered list. We need then 2 operations. L2 is times L1n. Each element of L2 is n times element of L1. We also need merge L1, L2. So we assume L1 and L2 are in increasing order, like here. And then we merge them. I'm assuming now a merge of 2. We could write a merge of 3, of course, but we can do merge of 2 and then merge another merge. That's a little easier. A merge of 3, the code is a little bit more complicated, huh? But if you want, you could write a merge with 3 arguments, huh? But since I want a simple merge, I've just used a merge of 2. So the result here contains the elements of L1 and L2 in increasing order. So this immediately gives us a program, and times and merge will be lazy functions, okay? This is it. This is the whole program now. The most complicated is the merge, huh? So here, for example, times S of H bar T, N times H, and times of Tn. So it just multiplies by N. Notice there's no nil case, huh? It goes on forever. You don't care, it's lazy. Notice how, look here how merge works now. S1 is 2. So S1 bar is 2. So we have, I put a bar because I need to take elements from both. So we have H1 bar T1 and H2 bar T2. If H1 is less than H2, then the output has to be H1. And we merge with T1 and S2, okay, since we advance in S1, but not in S2. And if H1 is bigger than H2, then the smallest is H2. And we merge, we advance with H2, but not with S1. And in the other case, they're equal. And there we have to advance in both, because we don't want any duplicates, huh? If we have 2 times the same number, we have to skip both of them, of course, huh? So this is the merge, a little bit more complicated. The actual main program is this. Look how simple it is. H is equal to 1, followed by, basically we have to merge the 3. We just have to merge these 3. So we have merge of times H2, and the second argument is a merge of times H3 times H5. And that's it. You could make it a little bit simpler if you had 3 argument merge, of course, huh? But then this one would be more complicated, huh? So there's no reason to do 3 arguments, but you can do it if you want, okay? And then you browse H. Now, when you run this, of course, nothing will be displayed, huh? So let me show how this runs. Okay. I think I'll just do start again. Since the system is lazy, but I am also lazy, so I have written the code here for having. So that's the times and the merge, okay? Then the actual program is this. See here, I just do it in one line, huh? Merge of times H2, merge times H3 times H5. I have to put it clear in front of H. That. So here it is. So far I have only one element. Huh? Let me this. If I want to see some elements, I can use touch, of course. Huh? Of course, I did not define touch. So let me define touch again. Here. So here we have the first 10 elements. 1, 2, 3, 4, 5, 6, 8, 9, 10, 12. Okay. But maybe I want more elements. H. Maybe I want 100 elements. Well, here we have 100 elements. Goes up to 1,536. Notice they can get spaced out more, huh? You have 1,000, 1,024, 1,080. So in the beginning you have everybody, huh? 1, 2, 3, 4, 5, 6, but they get more and more spread out, huh? Or if I want to use more than that. So here's more even. So up to 200 elements, I get up to 16,200. Okay? So this is very nice, right? It's very efficient. It's using memory which is strictly proportional to the number of elements we're computing. And the amount of computation we're doing is proportional to the number of elements, no more. So this is a completely efficient program. Okay? It's also very simple. If you want to write this, I would challenge you to do the same program in Java. Okay? Please, be my guest. Solve the Hamming problem in Java. I don't think the program will be so simple. Okay? Might be a good exercise to try that. I challenge you to do that. Okay? And to make it all as nice. So this is completely dynamic. Huh? It's efficient. It uses minimum memory and minimum time. Complexity is the best in time and space. Not bad, huh? For a declarative paradigm, huh? In the 1950s, this was state of the art, okay? This solution was something which was a major discovery. So Hamming, he had to invent this, but he did not have a lazy programming language in front of him. He had a he had Fortran and Lisp, basically. Lisp is not lazy. So it's harder to do that if you don't have lazy. So basically, the way to do this is you have to invent lazy evaluation. Okay, so it's not so nice. Okay, so let me go on now. Let me show you something which can help understand also the execution. Because if you just write this code, it looks very simple, but actually a lot of things are going on here, okay? Each of these lazy functions is creating thread, it's doing wait needed, and it's going back and forth. And so there's a lot of stuff going on here, okay? So sometimes it's nice to see that. And in order to see that, I'm going to talk about lazy suspensions, okay? It's just a graphical way of showing kind of what happens. Okay? So we have defined lazy evaluation using threads and wait needed. Okay? This is good, correct? But it does not really show the execution. Let's now show the execution in a graphical way. And I will introduce the concept of a lazy suspension. Well, a lazy suspension is just a thread waiting on wait needed, okay? It's just what we know already, huh? It's a thread that waits on wait needed. If you execute L2 is times L1, 3, when you run that, you will not execute the function. You will create a lazy suspension. And we write it like this. There's a variable here, huh? This variable, there's a thread waiting on this variable. We do it with the arrow. And what's inside this thread is this function call. Technically, it's the body of this function. So we write it like this. L2, there's an arrow and a little box. And inside, we write what it's waiting on. So there's a lazy suspension waiting on L2. Okay? So that's a way of like making a picture. And if you run the Hamming program, if you execute the program, you will create 5 lazy suspensions, and then you stop. So in memory, it looks like this. H equal 1 bar, and then you have a variable. So M1, it's an identifier, right? But it corresponds to a variable in memory, and there's a thread waiting on this variable, and inside that thread, there's the merge call. And in this merge call, we have two arguments, two more variables, T2 and M2. T2 has a thread waiting on it with this call. M2 has a thread waiting on it with this. So each of these variables, so the M1, T2, M2, they're all variables in memory, and each one of them has a thread, a lazy suspension waiting on it. So in memory, it looks kind of like this. Okay? When you run H equal that, you will create 5 threads, and they will all suspend. And that's it. It sits there. It just sits there like that. Okay? And now, if you want to execute this, you have to bind. You have to need something. So let's say I want to know the second element of H. I will do M1.1. Not the M1 is here, right? M1.1. So it's the same as H.2.1. Huh? Corresponds to M1.1. So if I do that, if I do M1.1, this will activate this lazy suspension, merge T2, M2, because there's a wait needed, of course, on M1. Okay. That will then continue. This will be run. So the body of merge T2, M2 will be executed. That's the definition, huh? The body of that one will be executed. So that gives you this. So let's say I do browse M1.1. I activate merge T2, M2. Okay. It executes the body of the merge. Well, what does the body of the merge look like? Let me go very fast here. So the merge body is a case statement. This is the merge, this is the body. So we go forward again. So the body of the merge is executed. It's this case statement of T2, M2. And here we have the case, H1, T1, H2 prime, T2 prime. I put a little prime here because I don't want to confuse this T2 with this T2. It's different. So the case statement, this is run now. The body is executed. But there's like a chaining happening because T2 is pattern matched with H1 bar T1. This will activate the suspension attached to T2. And M2 is pattern matched with H2 prime, T2 prime. This will need M2, so it will activate the suspension on M2. So that's the red one. The one waiting on T2 is times H2. The one waiting on M2 is merge T3, T5. So you see there's like a chaining going on. If I want the first element of M1, M1.1, this will activate the suspension, but it will continue activating more suspensions. So there's a whole chain of suspensions being activated. So these two will be activated. Times H2 and merge T3, T5 are also activated. That means the bodies of those two were also executed, and so on. Okay? Times H2 and merge T3, T5 are activated. So the body of times H2 is executed. So you can go on, but this will eventually result in T2 equal 2 bar T2 prime and a new lazy suspension. And if you do the merge T3, T5, this will result in M2 equal 3 bar M2 prime and a new lazy suspension. Now you can actually run the case statement because T2 and M2 are bound now. So T2 and M2, after these two suspensions run, T2 and M2 will be bound. So finally we can run the case statement. So the case statement will actually activate those two suspensions, But in the meantime, the case statement is still waiting, huh? And when those two suspensions bind their results, the case statement can continue. So you see there's actually some interesting kind of synchronization going on here, huh? The case statement activates two suspensions, and when they're done, it comes back and the case statement continues. Okay? I'm not inventing anything new here. This is all simply a consequence of how we, the translation of weight needed, huh? So there's, whenever you have a chain of lazy functions, when you need one, it will activate the next one, usually, and then that, and so on. So you have a whole chain. So just doing one thing here, just doing one thing, will cause a whole bunch of work to be done, huh? You see that, huh? In fact, all of these 5 will be activated, and they'll all run because I'm doing M1.1. So one simple operation, M1.1, will cause all of them to be activated. Okay. So you see, it looks very simple, but if you actually look at the execution, it's actually quite complex, sophisticated, huh? So finally, after T2 and M2 are bound, the case statement can finally run and returns 2 bar this, and so the result will be 2, the M1.1. But this recursive call will create a new lazy suspension. So basically what happens is, when I do M1.1, all 5 lazy suspensions are activated. They disappear, they're no longer suspended. They run, and they will create 5 new lazy suspensions. A little bit go on a little bit farther down the list. So whenever I ask for a new element, I activate 5 suspensions and I create 5 new suspensions. It's a lot of work, but it's all implicit. It's all hidden behind the lazy annotation. Okay? Just to explain it. This is nothing new. I'm just showing you the consequence of the definition we made. Okay? Okay. Let me now show you one more example today, which is called of a lazy program, a very sophisticated program. But first, I want to mention a little bit. I want to take a step back. The paradigms we saw. So what did we see so far? Well, we saw sequential functional programming. That was the first example. We saw deterministic data flow. This is with the agents, the streams. And then we saw lazy evaluation. Remember, with the program, with the producer-consumer, and you have infinite lists. But there's actually a fourth paradigm where you combine lazy and concurrency. Because lazy by itself, it's not actually concurrent. I mean, we define it using threads, but it's not actually doing concurrent because each function is evaluating and then suspending. So it's actually like a coroutining. It's not really concurrent streams, okay? We can actually use threads together with lazy functions. Threads and lazy functions. And this is a even more powerful one. And so I want to show you how that works, okay? It is the most powerful declarative paradigm that we're going to see in this course. It has 3 special powers. It has confluence, and higher order, of course. It has concurrency, independent activities, agents, and it has lazy, by need. And those are 3 powerful things. With all this power together, we can do things that we could not do otherwise. Okay? So notice that there's almost no language that gives you this. So Haskell actually, which is doing lazy, it does not actually do this because it's not doing deterministic data flow. It's only doing lazy Haskell. So this is the most powerful, and it's more and more being used. You will see this one in the future. Okay, so I'm touching on it now, and you will see it more and more being used in the future. Okay, but I want to give you one example of this. It's actually a very simple concept called bounded buffer. You can write it in a declarative way if you do lazy deterministic data. Okay, so a bounded buffer is actually something you see in many courses. I mean, if you want to do TCP, network protocols, you will have buffers. If you have processes talking to each other in Unix, they will be buffering. Buffers are used everywhere in computer programs, okay? And so first I'm going to explain why buffers are useful. And then I'll show you how to program it. So here's a simple producer-consumer. And it can be many things. It can be two processes on the computer that are talking to each other in Unix or whatever, Mac OS, or Windows. Or it can be two computers on a network sending packets to each other using TCP. Any kind of producer-consumer. So this is very common. Many, many places you see this. Okay, it's a very general thing. But this simple pipeline here with two things, it has problems. It can have problems. So here, let me explain how it works. The producer and the consumer, they're not executing at the same speed, usually. And they have fluctuations. So if the producer executes elements too quickly, the consumer cannot use them. So the producer has to wait until the consumer can use them. So that slows down the producer. Okay? If it's too quick, if the consumer cannot use the elements, the producer has to slow down. But if the opposite, if the consumer needs elements, I can use it right away, but the producer is slow, then the consumer has to slow down. So the two are kind of slowing each other down. You see that? This kind of mismatch. Because the speeds of those two are fluctuating. And it happens in many, many things. It happens in video streams, process communication, networking. Everywhere you have this happening. Okay? So what's the solution? So the problem here is that the producer has to slow down because the consumer cannot use the element right away. Or the consumer has to slow down because the producer is not giving it an element. So each of the sides will be slowing down whenever there's a fluctuation. So how do we solve this? So the solution to this problem is called bounded buffer. Okay? So this is independent of paradigms. This is very general. Whenever you have producer-consumer that have different speeds and different fluctuation, if you want to smooth it over, improve the performance, all you have to do is stick in a bounded buffer in the middle. Okay? So we stick a bounded buffer, it will solve most of these problems. Okay? So if the producer is making elements too fast and the consumer cannot use them, it's okay. We put them in the buffer. So the producer can keep going, even though the consumer cannot take them. And in the opposite direction, let's say the consumer needs elements, but the producer is not making any. But maybe they already are elements in the buffer. Just take them from the buffer. Okay, the buffer will store them. So the buffer is kind of smoothing things over. It lets the producer produce elements too fast, and it lets the consumer consume elements even if the producer is not producing them. So it smooths out the fluctuations, the producer-consumer, and it will improve performance. So a bounded buffer is used very often. It's like matching the two sides. See that? See, the bounded buffer is actually matching these two, and it's very, very common concept. So you will see it in many, many, many courses, not just with me. Okay? But I want to show you that in order to I want to program the bounded buffer. And in fact, you do not need to program it using state, or you can program it completely declaratively, and that's something many people don't know. The bounded buffer can be done in a completely declarative way, which makes it very much a better piece of code. Okay. Okay. So what we're going to do. So the bounded buffer here, you can write it in Java. Maybe you've already done a bounded buffer using linked lists or whatever, and using pointer updates, It's not declarative. But it doesn't have to be like that. You can actually write the bounded buffer in a completely declarative way. Okay? Using lazy dataflow. The way we do it, assume we have a producer and a consumer, and they're both lazy. So the producer-consumer are both lazy. This is fine. And the code is the same as if there were no bounded buffer. Okay, we just stick it in between lazy producer and lazy consumer. And in fact, from the viewpoint of the producer, the bounded buffer looks like a consumer. Okay, and from the viewpoint of the consumer, the bounded buffer looks like a producer. So the producer and the consumer, they don't see any difference. The producer still thinks he's sending things to the consumer, and the consumer still thinks he's taking things from the producer. Okay? So the bounded buffer can consume elements from the producer, even when the consumer does not ask for them. So the producer can send elements to the bounded buffer, even though the consumer is not asking and cannot use them. But that doesn't have to slow down the producer. They can just put it in the bounded buffer. And in the other way, sense, the consumer can take elements even if the producer is not making them, because they're already sitting in the bounded buffer. Okay? So this will improve the performance, smooth out the system. This piece of code, usually it's written kind of non-declaratively, with state, for example, variables you can update. But you don't have to. This can be written completely declaratively, and I will define it for you now. Okay? But first, let me show you the use, the scenario. Okay? So we have a producer here, producer agent, and a consumer agent, and S is the stream in between. Okay? And they're both lazy. We put the bounded buffer in between them. So S1 comes from the producer. It goes to the bounded buffer. The bounded buffer outputs S2, which goes to the consumer. So instead of S here, going from producer to consumer, we have S1 going to the bounded buffer and S2 going to the consumer. And now I can write the code for this procedure, bounded buffer. So here we have a bounded buffer call with two streams, input, output, and a size. So the bounded buffer, it's bounded, so it has a fixed size, a maximum number of elements that can be stored. This is very reasonable, because the bounded buffer will be sitting in a piece of hardware usually, and there's a fixed memory in there. So you can't just make it go arbitrarily big. You have to fix the size to some maximum. So the maximum size here is 10, for example. Okay? So now let me show you how to write this code. And we're going to define it step by step. And hopefully this will help you understand how it's working. Because the code is actually kind of subtle. But if you do step by step, it should be easy. Okay, so we're going to define this procedure, bounded buffer. S1 is the input stream, S2 is the output stream, and N is the size. And we're going to do it in 4 steps. Okay, so I'm going to make first 4 steps. So here's the procedure, and in red I will put in the code that I'm adding. Okay, so the first step is easy. All the elements coming in S1, they have to go out. The bounded buffer does not change any elements. It does not reorder elements. All the elements coming in have to go out. It's logical. It's just they go out at a different time, but they go out. So we will define a lazy loop here, which reads S1, and when it finds an element on S1, it passes it to the output. It's very simple. See? Case S1 of H1T1. Okay? And then the output is H1 bar loop T1. So all the elements coming in on S1 go out. So the loop is like doing nothing, huh? It's no off. But it's a lazy function, and we're going to build something on that lazy function. Okay? So that's the first thing for the bounded buffer. But we need to do more now. Okay? And the next step is when it starts up. When I start up the system, now, the bounded buffer will immediately ask for n elements from the producer. The bounded buffer is empty when it starts up. So it will immediately ask for n elements, which means eagerly, from the producer, so that it can fill up. So it's running this. So I'm using a built-in function, a list.drop, which basically removes the first elements from S1. So it's traversing S1, n. And the end is where it ends up. And this is not lazy. So immediately, S1, it will need n elements when it starts up. Because the buffer has n elements, we immediately want to start filling it up when it starts. Okay? And so the red, and of course you have to declare it. That's good, right? That's reasonable. And then those elements, once they're there, the loop can read them, of course. The S1 will be bound. They will be needed and they will be bound. Okay? The second step is while it's running. Whenever the consumer asks for an element, that removes one element from the buffer, which means the buffer has to ask the producer for one more element in order to stay full. Okay? So whenever the consumer takes an element, that's an iteration of loop. Oops. Here, that's an iteration of loop. This is run whenever the consumer needs an element. Well, it has to ask the producer for another element. But that's easy enough. We add an extra argument to loop, which puts in this end, and we run it with end.to, which asks for the next element from the producer. Okay? That means whenever the consumer takes an element, it will automatically ask the producer for another one. Maybe the producer cannot give it, but we don't care. We have to ask for it, so the buffer tries to stay full. Whenever the consumer takes an element, it asks for one more from the buffer. And then there's a final step, because there's a problem with these two steps. These are sequential blocking. The final step is we have to put those two things in their own threads, because otherwise they will block. End.to will block until the producer makes an element. But we don't want that to block everything. So we create a thread. Remember, the thread is the unit of waiting. We let some other thread wait. So it's very easy. We just put these two operations in their own threads, and we're done. That's it. This is the whole code. This is the final code. Okay? So you see, it's basically a loop which does nothing with a mechanism for filling up. A mechanism for filling it, and a mechanism for staying full. Okay? And that is the bounded buffer. Okay? Okay, let me end there, and then next time I show it running. Okay? And then next time we get the pièce de résistance, as they say in French. Next time I will show you how lazy evaluation can invent algorithms. I will take a quicksort algorithm and turn it into lazy quicksort. And the lazy quicksort is like a magic, amazing algorithm and it's automatically created by lazy. So lazy can sometimes be very, very smart. Okay? So that we will see next